Hello students, we are now in lesson 10, the central limit theorem. If we want to get a good estimate of the population mean, we have to make n sufficiently large. That is what is being stated in the central limit theorem. According to the theorem, if random samples of size n are drawn from a population, then as n becomes larger, the sampling distribution of the mean approaches the normal distribution regardless of the shape of the population distribution. So the central limit theorem assures us that no matter what the shape of the population distribution of the mean is, the sampling distribution of the sample means is closely normally distributed whenever your n or your sample size is large. For samples of size 30 or more, the sample mean is approximately normally distributed. Basically, the larger the sample size, the better the approximation. So in a population, the values of a variable can follow different probability distribution. These distributions can range from normal, right skewed or positively skewed, left skewed or negatively skewed, and uniform distribution among others. So let's start with the normal distribution. The normal distribution has a central peak where most observations occur, and the probability of events tapers off equally in both the positive and negative directions on the x-axis. So basically from the mean, you can say that 50% of your data is above the mean and 50% of your data is below the mean. So both halves contain equal numbers of observations, and unusual values are equally likely in both tails. Right-skewed distributions occur when the long tail is on the right side of the distribution. Analysts also refer to them as positively skewed. This condition occurs because probabilities taper off more slowly for higher values. So consequently, you'll find extreme values far from the peak on the high end more frequently than on the low. Left skewed distributions occur when the long tail is on the left side of the distribution. Statisticians also refer to them as negatively skewed. This condition occurs because probabilities taper off more slowly for lower values. Therefore, you'll find extreme values far from the peak on the low side more frequently than on the high side. So regardless of the distribution of the population, as the sample size is increased, the shape of the sampling distribution of the sample mean becomes increasingly bell-shaped, centered on the population mean. Remember, normal distributions have two parameters, the mean and standard deviation. As the sample size n increases, the standard deviation, or often called the standard error of the sampling distribution, becomes smaller. Thus, the sampling distribution clusters more tightly around the mean. For our next examples, let's practice finding the mean and the standard deviation of our normally distributed populations. For the first problem, a population has a mean of 60 and a standard deviation of 5. A random sample of 16 measurements is drawn from this population. What would be the expected mean and standard deviation of the resulting sampling distribution of the sample mean? To solve for this problem, let's first identify what are given in our situation. So first, let's identify what is our population size. The population size is unknown since there's no way of finding how many are there in the population. Our sample size is 16, our mean is 60, and our standard deviation is equal to 5. Now we're going to find the mean of the sampling distribution of the sample means. Now since the mean of the sample means is equal to the population mean, so our mean is equal to 60. Now let's solve for the standard deviation. And since our population size is unknown, we are dealing with an infinite population. So the formula in finding the standard deviation of our sample means for infinite population is given by population standard deviation over square root of n, or the sample size. So we just substitute the values. That's 5 over square root of 16. Square root of 16 is equal to 4, so 5 divided by 4 is 1.25. Hence, our standard deviation for the sample mean is 1.25. Let's have the second situation. The mean and standard deviation of the tax value of 500 vehicles registered in a certain city are 13,525 pesos and 4,180 pesos respectively. Suppose random samples of size 100 are drawn from the population of vehicles. What is the standard deviation of the sample means? First thing that we need to do is to identify the given. So our population size is 500. The sample size is equal to 100. The population mean is 13,525. And the population standard deviation is 4,180. Now, since the mean of the sample means is equal to the population mean, hence our mean of the sampling distribution is equal to 13,525. And we are asked to find the standard deviation. So remember that we have here our population size. We have the value of the population size. So we are dealing with a finite population. So the formula in finding the standard deviation of the sample means for finite population is given here. Now we just need to substitute the right values in our formula and make sure that you are not confused with substituting the values. And then next, let's simplify. The square root of 100 is equal to 10. 500 minus 100 is 400. And 500 minus 1 is 499. So let's simplify further. 4,180 divided by 10 is 418. The square root of 400 over 499 is 0.8953229621. We multiply the two values. The final answer is 374.24. This is being rounded off up to two decimal places. Hence, that is or this is the standard deviation of our finite population. So that's it for today's lesson. I hope you learned something about the central limit theorem and how to find the mean and standard deviation of your normally distributed population. Always remember, have a statistic amazing day.